All right. I want to talk now about significant results. We're getting very close to the point where significant results are more than just a little bit of a calculation to do within a problem. Identifying significant results will be very, very important when we start to explore inferential statistics. We haven't really done that just yet. That will really start in chapter 7. We lay the groundwork for it in chapter 6. It really takes off in chapter 7. So identifying and understanding what we mean by a significant result will be really important. Now, in terms of a binomial distribution or any other kind of discrete distribution, when we're talking about the number of successes or the number of outcomes that meet a particular criteria, there's a couple of ways of going about that particular process. We can take a look at it from a probability perspective, and that's what I really want to emphasize here. So if I want to find the probability of a significantly high number of successes, I want to find the probability that X is at least this many number of successes. That's in terms of the number of successes that I need, and I need a probability that's less than or equal to 0.05. When I'm looking for significantly low numbers of successes or outcomes, the question we really want to answer, the probability that X is at most some particular number of successes or failures or outcomes, and that probability needs to be less than 0.05. Now, this can be confusing because we already have a way to identify significantly high numbers or low numbers of outcomes. We have the mean plus or minus 2 standard deviations. These two methods are equivalent. They really don't produce different results. So, at least not in most cases we are concerned with here. So, let me run through exactly how this might look in each circumstance. And we're going to take a look at a sample size of n equals 20. So we've got 20 random births. X is going to be the number of girls that we are interested in. The probability of a girl in any one randomly selected birth is 1 out of 2 or 0.5. Now, using our formulas, n times p times q square root for the standard deviation, I get those units in there. I'll get 10.0 girls for the mean number of girls in 20 random births, and I will get 2.2 girls for the standard deviation with the number of girls in those 20 births. Now, I've rounded the standard deviation to 1 decimal place, and I'm calculating the mean plus or minus 2 standard deviations. So that's 10.2 plus or minus 2 times 2.2. On the low end, that's 5.6 girls. On the high end, that is 14.4 girls. So I've got a quick number line here. 10 is essentially right in the quote-unquote middle, if you will. If you march up down to 5.6 and up to 14.4, these are where births become significantly low and high, respectively. Now, I'm going to jump over to my calculator in just a moment to run through the keystrokes, but I'm pointing out something here. The probability of at most 5 births. I'm going to run that calculation on my calculator. It should come out to something like a 0.0207 with rounding. Then I'm going to run the same calculation, but 0 to 6 girls in the 20 random births, and that probability will come out to something like this. So let me go ahead and jump over to my calculator and share my screen so I can run these keystrokes by y'all one more time. All right, so I'm going to remind you that what we're using is the binomial CDF function, because I'm calculating the probability of 0 or 1 or 2 or 3 or 4 or 5 for the first one, and then 6 for the second one. So that's distributions. Second distribution. I find my CDF. I've got 20 trials. The probability of a girl in any one trial is 1 out of 2. 0 through 5. That's how this works. We'll paste that into the function and it will just take off and run. I'll hit enter one more time, and I can see that we got a probability of 0.02069. That's 0.0207. When we go out 3 significant digits, there's the first non-zero is 2. The third one is the 6. The 4 is a 9. So there we go. Now, if I run the same calculation, but I go and throw in one more success, paste that in, there's a 0.05765, so 577. Now, let me stop my sharing. Come back here. And I note that in the first case, that probability is less than 0.05. So 5 or fewer is significantly low in terms of the number of successes, or girls in this case in 20 births. On the other hand, the probability of 6 or fewer is greater than 0.05. And I will note, by the way, that 6 appears out here. 6 is bigger than 5.6. So it comports with that plus or minus 2 standard deviations, at least the minus. Now, let me go ahead and take a look at this guy here. Students usually struggle more with this type of calculation. Why? Because of the way your calculator works. I will remind you before I turn my calculator back on that we need the complement. The complementary argument for this to work on our calculator. And again, I got a number of videos that demonstrate this, and then you'll be able to watch this one too. So I want to find the probability of 15 or more. that's 1 minus the probability of 14 or less. The 20 and the doesn't change, the 1/2 doesn't change. So this is the probability of 0 up to 14 girls. The flip side of that is 15 or more. There's the 1 minus. There's a 0.02694. Notice how it mirrors this guy up here, and I'll explain why in just a few moments. On the other hand, if I want to throw in one more success, that means 14 or better. So this time, "13 or fewer." Paste them in. And there's the 0.0577 again. I'll explain why that works the way it does in a moment. But there we go. Let me stop my sharing, because again, I want to pick that up here. That again, in the first case, we are less than 0.05, and in the second case, we are greater than 0.05 for those probabilities. There's the 14, there's the 15, not 13. There we go. So again, it really does comport, and whether you use the mean plus or minus 2 standard deviations or the probability argument, you should be able to get to something that's the same in both cases. I will say this, that it's usually easier to use the probability argument. That's the one you're going to see much more often than the mean plus or minus 2 standard deviations. There are times that actually does not work, but it's kind of weird data sets. So let me just really stress what went on there. So here I redrew the picture, and I will note that that 10 is in some sense right there in the middle. And if we go up, the +2 standard deviations and down -2 standard deviations is where we pick up the 14.4 and the 5.6. So 15 or more girls, 5 or fewer girls. That's where we draw the line. Now, let me tell you why this gets used, or at least one way it gets used. For example, some parents want to make sure that they have children of a particular gender. So there are particular processes you can go through to up the probability of having either a boy or a girl. So these things are not cheap. If you're going to pay for something like that, I think you would want some proof. You might say to them, well, suppose I picked 20 births at random that you guys worked on. I know that I should have somewhere in the neighborhood of 10 girls in those 20 births. Oh, you claim that you can give me 15 girls in those 20 births? Ah, maybe they've got something that might really work. Won't be a guarantee. And they'll make you sign a whole bunch of stuff to that effect, I am sure. Now, let me talk just a little bit about why we had the symmetry in the cutoffs probabilities. I will note that for n equals 20 and p equals 1/2, possible outcomes range from 0 at the low end to 20 at the high end. The highest probability is right there in the middle, is 10, and it drops off in a very, very bell curve type of fashion. In fact, it's well approximated by a bell curve. So here you are out here at 15 burrs, and down here you are out at 5 burrs and less. So this probability and this probability here, less than 0.05 in both cases. So that was why we were seeing the symmetry. Furthermore, this is what the P actually does to the distributions, the probability distributions. I'll put together a little bit of a presentation, I think, for Monday on this. It's kind of hard for me to demonstrate this directly. But I will note that, come here. Suppose we're still working with n equals 20. This time I've got p equals 1 out of 4. N times p is 20 times 1/4, or 5. So the probability distribution would have its tallest member, or the highest probability, at 5, but it would then drop down like that, and it would really tail off here as it got up to 20. And that would that would go back the other way too. Suppose we had p equal 3/4. Mu is equal to 20 times 3/4 equals 15. So the outcome with the highest probability would be up there, and then they would fall off gradually down to 0. That is. So that hump, if you will, moves left to right depending on p, as p goes from small to large. The hump. By the way, the hump is not a technical mathematical term, but that's what I call that. I call it the hump. So there you go. Now, I'm going to finish this up with a little bit of summary on your calculator and what we've used so far and how we've used it. This list is going to get long. So in 5.1, when I had a given probability distribution, I used the 1-var stats, and we had 2 lists. List 1 were the x values, list 2 were the probabilities. That's where that frequency comes in your stat wizard. We usually like to round those summary statistics to one decimal place, because the variable is a whole number, 0, 1, 2, 3. Remember, it's the mean, mu, the standard deviation, sigma, and the variance, sigma squared. And I use those rounded values, or I can use my table too to determine cutoffs for significant scores. The mean plus or minus 2 standard deviations. Now, in 5.2, I use the Binomial Cdf function to calculate the probability of exactly x successes. And the book, honestly, is really consistent in their use of the language. They're not too, they don't try to get tricky with this type of problem for the most part. If we have to calculate the probability of at most or at least, I use that Binomial Cdf function for the at most. And I'll remind you, for these, we'll give them n, p, and x. So you go from 0 up to x for this cumulative one. So that gives you P of 0 plus P of 1 plus P of 2 plus P of all the way up to P of X. If we need to calculate at least or more than or something of that nature, I need to use the cumulative distribution and the complementary argument, the 1 minus binomial CDF, to calculate the probability of at least X successes and N trials. And just to make sure you really know what I mean by that, again, at least X successes and N trials. So that's 0, 1, 2, 3, all the way up to N. X is there somewhere in the middle. This is the set that you are interested in. This is the probability of A you want. But your calculator can't do that. It's got to work with the complementary argument because the cumulative distribution function starts at 0 and it counts up to, in this case, X minus 1. So it's 1 probability of 0 up through X minus 1. That's horrible notation. Don't look at that. Don't look at that. There we go. So, and that's the one that honestly is the most tricky out of the entire 5.2 material, that particular kind of question. Other than that, you guys do pretty well with the 5.1 and the 5.2 material, provided you do one thing, provided you practice. So let me go ahead and stop my recording.